Alright, my calculus students, first thing we're going to do today, we're going to be taking the derivative of the natural log of x. We're going to find that it's 1 over x. As a quick reminder here, the domain of the natural log of x is from 0 to infinity. If I want you to graph it on Desmos just to verify this. So pause the video, graph it on Desmos. You'll see the domain is all the x values, which go from can't quite equal 0, but goes all the way up to infinity. And the range goes from negative infinity to infinity. So I'll give you a second just to pause the video, look that up in Desmos. Next thing you're going to do, since you're done with that, is you're actually not going to be doing any of these problems yet. I want you to review the properties of logarithms, condensing things, expanding things, and to do that, quiz trade cards right here. So there should be a stack of these on my desk, and you can grab the quiz trade cards here. You can split them up into sections. You can walk around classroom and do it. You can do it in your group, but just make sure that you are reviewing the properties of logarithms here. So condensing things and expanding them, writing in a different base. The answer, of course, is on the other side, and also simplifying just some basic ones here. Like log base 2 of 8 would be 3. Because 2 raised to the third is equal to 8. So logarithms, if you remember, find the exponent. Logarithms find the exponent. All right, so quiz trade cards. Pause and go do that. Now that you are done with the quiz trade cards, and we'll do these beginning of the lessons, a couple different lessons here. We're actually going to be using this. So a lot of the skills we're going to be using here, we're going to be taking the derivatives of new functions, but the same basic tasks are involved here. For example, find the relative minimums and maximums. Any points of inflection for y is equal to x times the natural log of x. So, to find minimums or maximums, I'm going to take the derivative. Now, I've got a function times a function here, so I'm going to use the product rule. Derivative of the first is 1 times the second, natural log of x, plus the second, x, times the plus the first times the derivative of the second. Derivative of the second here, natural log of x, we know is 1 over x. So when I derive this, I'm going to get the natural log of x plus x times 1 over x is just 1. That's pretty simple. So, got to find when there are any relative minimums and any relative maximums. To do that, I have to set it equal to 0. So when does the natural log of x plus 1 equal to 0? That's just like saying when is the natural log of x equal to negative 1. Now to get rid of this, I'm going to exponentiate both sides. So x is equal to e to the negative 1, also known as x is equal to 1 over e. Now, to check to see if this is a minimum or a maximum, I'm going to pick numbers on either side here. Now, the easiest number to pick that's bigger than 1 over e, how about we just go with e? Y of e, if I plug that in, y prime of e. So if I plug it in over here, natural log of e would be 1. Plus 1, which would be 2, which would be greater than 0. So the function would be increasing. And if I choose something smaller than e, how about I choose 1 over e squared? Well, that's going to give me 1 over e squared is, since I can rewrite this as y prime is equal to e to the negative 2. And I plug that in here. That's just going to give me -2 plus 1, which is -1, which is less than 0. So that is decreasing. So since y prime changes from negative to positive at x equal to 1 over e, y has a relative minimum at x is equal to 1 over e. All right, now checking to see when it has any points of inflection here. Let's do this on a slightly different piece of paper here. For this, we knew that y prime was natural log of x plus 1. To find points of inflection, I have to take the second derivative of the original function, so I'm going to derive that again and get 1 over x. And I got to find out when 1 over x changes from positive to negative. To do that, I'm going to find out when x is 0 or undefined. Well, this will, when will this equal 0? Never. It will never equal 0. Will never equal 0, and it will be undefined when x is equal to 0. But if we look at our original here, we know we can only plug in numbers bigger than 0. So what we really have here is this function right here is always going to be, I can only use numbers greater than or equal to 0, because that's the domain of this. And since I can only use numbers bigger than 0, y double prime, which is 1 over x, will always be greater than 0. Correction, just greater than 0. Since it's always greater than 0, we know it's always going to be concave up. All right. In our next problem here, we've got to find the equation of a perpendicular line to f of x when x is equal to e. Now this part right here looks big and scary, and take the derivative of all that. But once we use the properties of logarithms, we realize if I can start with this, and then since I'm dividing, I can subtract that. And then, because of the properties of logarithms, I can take this 2 and bring it down in front. This is just x plus 1 to the 1/2. I can bring that down in front as well. So this right here is much, much easier to derive. 2 times the natural log of x, well, the derivative of the natural log of x is just 1 over x. Then 1/2 times the derivative of x plus 1, the natural log of x plus 1, just be 1 over x plus 1. Then we got chain rule, take the derivative of the inside 2, times 1. So after some simplification here, 2 times 1 over x, just 2 over x. And I distribute this down here, 2x plus 2. So the slope of a tangent line is going to be 2 over e minus 1 over 2e plus 2. But we're not trying to find the slope of a tangent line, we're trying to find the slope of a perpendicular line. So the slope of a normal line. To do that, we're going to have to fraction flip and change the sign. Now we're not going to go through all the simplification here, but suffice to say the slope of a perpendicular line is going to be 1 over 2 over e minus 1 over 2e plus 2. So we got to flip that fraction and change the sign. So that's the slope of the perpendicular line. All right. And because our equation is actually y minus y1 is equal to m times x minus x1, so we're going to do x minus e. And f of e would just be this thing right here. That's the y value. So we're going to get y minus the natural log of e squared over the square root of e plus 1. Now, could I simplify that down if I want to? Oh, sure I can. Not going to, though. I'm just going to leave it right there. That's the slope of my perpendicular line. In the next problem here, we got to find the derivative of f of x here. F of x is equal to the natural log of x squared times the quantity 4x squared plus 2 cubed all over the square root of 6x to the fifth minus 7. This looks horrible. Horrible, I say. But it's not, because we can expand this using logarithms. Everybody loves a log. So we're going to get the natural log of x squared plus, because it's multiplied, natural log of 4x squared plus 2 cubed minus the natural log of 6x to the fifth minus 7. And we're going to simplify it even more. 2 times the natural log of x plus 3 times the natural log of 4x squared plus 2 minus 1/2 the natural log of 6x to the fifth minus 7. Now we're actually going to derive it. F prime of x would be 2 times the natural log of x, which is just 1 over x, plus 3 times the natural log of x is going to just be 1 over whatever's on the inside, 4x squared plus 2. But because of the chain rule, we got to take the derivative of the inside here. So the inside is going to be 8x. And then we got to take the derivative of natural log of 6x to the fifth minus 7. And get 1 over 6x to the fifth minus 7. Chain rule. Take a derivative of the inside here. Derivative that's going to be 30x to the fourth. And you can't take the derivative of 7 there. So let's do just a little bit of cleanup here. We get 2 over x plus 24x over 4x squared plus 2 minus, let's cancel that out, make it 15. That sounds a little better. 15x to the fourth over 6x to the fifth minus 7. We could cancel a 2 out of here if we want to as well, but you know what, we'll just go ahead and leave it right here. So we see here that if we have a natural log on the outside, that makes taking the derivative a whole lot easier. But what if right down here, we don't have a natural log on the outside? We don't have a natural log to make our lives easier if we have to find the derivative. Do we freak out? No, not at all. Here's what we do. We're going to call this side y. X times x minus 1, 3/2, sine of x over the square root of x plus 1. Now, if we take derivatives and there's natural logs, we can use the properties of logarithms, but there's no natural log. That's okay. I'm going to hit both sides with a natural log. Just going to slap that on there. Now, got to take the derivative of both sides. Well, what's the derivative of the natural log of y? It's going to be 1 over y dy dx. because we're deriving with respect to x here. We've got to find f prime of x. So we've got to have the dy dx on there, implicit differentiation. Now I can make this nice and beautiful. Natural log of x plus the natural log of x minus 1 to the 3/2 plus natural log sine of x minus the natural log of square root of x plus 1. Now, I simplified this side. I still have to take the derivative of this. But I'm going to go ahead and continue to simplify this. Still haven't taken the derivative. That's okay, though. Natural log of x plus 3/2 natural log of x minus 1 plus natural log of sine of x minus 1/2 natural log of x plus 1. Running out of room here, sorry about that. And now I'm going to go ahead and hit this with a derivative. 1 over y is equal to, so dy dx is equal to 1 over x plus 3 over 2 times 1 over x minus 1. Chain rule, derivative of the inside here is just 1. Nothing to worry about there then. Derivative of natural log is 1 over whatever's inside, sine of x, times the derivative, which would be, derivative of sine of x is cosine of x, minus 1/2 of 1 over the square root of x plus 1. Oop. Not the square root, sorry. Now, you may be saying, well, Mr. Kuhne, we have to find the derivative with respect to x. We've got to find f prime, or just dy dx. How do I get rid of this y? Well, let's bring it over to the other side. Let's multiply both sides by y. So that will cancel that out. And you may say, but Mr. Kuhne, it has to be a function of x. Well, if only we knew what y equaled. Oh, we do know what y equals. Let's look back in the original problem. Oh, it's right there. It's right there. So the derivative, dy over dx, which is really just f prime of x, is equal to this whole thing. Let's see here, 3 over 2x minus 2. Cosine over sine would be cotangent of x, minus 1 over 2x plus 2, times the original function. And that's our answer right there. Now, you may be saying to yourself, Mr. Kuhne, that's a lot of work. It really is a lot of work. You're correct. But this just goes to show you some cool things that you can do with logs. Makes taking big, long derivatives a whole lot easier. A whole lot easier. Logs would have been very, very useful on your derivative Olympics problems. Just hit both sides with a natural log, expand it, take the derivative, and it's a piece of cake then. You won't find any problems like this on the AP exam, but I'm showing you this just for the fact that this is cool. Hit both sides with a log, expand it, take the derivative of it, of both sides, and because this is 1 over y, I can multiply both sides by y, and then just plug the original function, which is y, back into it. So mostly that's just showing you a cool process right there. You might have 1 or 2 homework problems like that. Nothing super hard though, but there won't be any AP problems like that. So that's how you use, that's how you take derivatives using natural log. Thanks for watching.